In this video we're going to go through how you use bond enthalpy, or bond energy as it's sometimes called, to work out the enthalpy of a reaction, so delta H for a reaction. I'm going to go through an example here because I think it's probably the easiest way to learn it. Basically, bond energy is the amount of energy required to break a bond. If you want to think of something a little bit sad, there's a song called Breaking Up is Hard to Do, so it takes a lot of effort. So you have to put energy into breaking a bond. There you go. Lame, but you'll remember it now, won't you? So bond enthalpy is the amount of energy required to break 1 mole of a particular bond. Whether it's an oxygen-hydrogen bond, carbon-hydrogen, carbon-carbon single bond, whatever. It's the amount of energy required to break 1 mole of those. It's a whole mole of them. Therefore, its unit is kilojoules per mole. The energy is the kilojoules, the per mole tells you the amount of them. They're used to find the enthalpy of a reaction, and it's actually the standard enthalpy usually. And again, that would be given in kilojoules per mole. So you've got to make sure that something to start with is in only 1 mole of it. Okay? If it's not, then the answer will just be kilojoules. So if I had a 2 in front of that, for example, for the balanced equation, then it wouldn't be per mole, it would just be kilojoules. Okay? Just like the work we've done before, you should be able to predict whether it's exothermic or endothermic to start with, which really helps in doing one of these sorts of questions. This is an example of combustion. And combustion is another word for burning. And we should all know that burning releases heat energy, so it's exothermic. So the little note I'm going to give to myself here is that it's exothermic. The reason I'm going to remember that is that my enthalpy for the reaction should be negative. Even though the values I'm given are positive, I need to somehow get a negative answer. Okay, so delta H is going to be negative. So I've just written that down as a wee note to self. It's going to be it's combustion, so it's exothermic, so it's going to be a negative enthalpy for the reaction. In the work we've done so far, we learned about a thing called activation energy. Put simply, activation energy is the amount of energy required to break enough of these bonds for this reaction to occur. It might not be all of the chemical bonds, but enough of them for this reaction to occur. However, if bond breaking is hard to do, if breaking up is hard to do, so if bond breaking is endothermic, you have to put energy into it, then what do you think bond making might be? Exothermic, good. So these ones, when they form, actually release energy. And the reason for that basically is that a bond is made to make the atoms involved more stable. That's why bonds are formed. So they're going to have a lower enthalpy because they're more stable. If I break these up into their atoms, I'm making it less stable, so I need to add energy. It's endothermic. So simplistically, that's the reason. Again, we're assuming no change in pressure, so this would be linked to our heat change. So the way that I think of this is a bit like a ledger. These have to be broken, these have to be made, and that'll give me my exothermic value over here. So it's this minus this, because negative for exothermic. These bonds broken minus these bonds made will give me my enthalpy of reaction. But to do that, I kind of need to know what these look like so I know which ones of these I'm going to use. By the way, in a question you're given these, and you're often given ones that are not involved as well, so that you have to choose the right ones. Like they might have an OO single bond, they might have data for that as well. To check that you actually do realise that oxygen, O2, is an OO single bond. I've actually forgot to put one up, I'm sorry, which is the CO double bond. So I'll just quickly add that now, which is 724 kilojoules per mole. So I'm going to draw all of these out. This is why I've done Lewis diagrams and stuff like that in the same unit, because if you can't draw them, then it's pretty hard to know which bonds are broken. So we're going to do that very quickly. CH3, CH2OH, so ethanol, is going to look like this. It's got 2 carbons, you can be pretty sure there's at least a single bond between them. And every carbon makes 4 chemical bonds. Well, if I look at that, that's got 3 hydrogens around it. Oh, good. Okay, so that therefore must only be a single bond. Put 2 hydrogens next to this one. Whoops, sorry. Then it's got an oxygen. Oxygen has a valency of 2. We should know from our Lewis structures now. So it's going to look something like that. Our oxygen, if oxygen's got a valency of 2, you're going to need a double bond between them. So they've both got 2 bonds. Okay? And there's 3 of those. So these are the bonds that, sorry, this is the stuff that has to be broken. 1 of those and 3 of those because of the 3 in here. Remember, these numbers mean the number of moles that are present if I'm assuming I had 1 mole of this. 1 mole of this, 3 moles of this, 2 moles of this, 3 moles of this. So I love using colours, so I'm going to go use some colours over this side too. So there are the things being broken up. These are the things being made. Carbon dioxide, again, carbon has got a valency of 4, so it must have double bonds to the oxygen. So that's got 4 bonds. Oxygen's got 2 bonds, so that's good. It says 2, so I'm going to draw 2 of them. And then water we should know pretty well now. And again, I'm drawing 3 of them because there's 3 there. If you see that any of these have got funny numbers like 2.5, which they might do, then don't draw 2.5 of them. Draw 3 of them, but maybe put a bracket around in the 3rd one, just to remind yourself that it's not a full one. Because these are moles, they're not numbers of molecules, they're moles of the molecule. So you can have half a mole quite realistically. Okay, so this is good when you've got whole numbers, and I'm pretty sure in level 2 you'll only be working with whole numbers.
If it was 2.5, would you be able to draw 5 and then double everything?
That's what I'd do, yeah. And then in your final answer over here, you'd have to divide that by 2. It's a really good way to do it. So now my next thing is I need to find out what's being broken. And the easiest way is to break everything and make everything. While you're learning how to do this, that's my suggestion. Calculate every bond that's broken, calculate every bond that's made, and then go this number minus this number equals the answer. When you get good at it, you'll start recognising, oh, there's an OH there, so I cannot calculate one of those, as long as I don't calculate it on both sides. But while you're learning it, break everything, make everything. It's slower, but it's more likely to be correct. So, I'm going to identify a bond, find out how many there are. The first bond I'm going to look at is the CH bond. There's 1, 2, 3, 4, 5 of those. So I'm going to write 5 times, here's CH here, 414. I'm not going to worry about my units, this is just my working. So I'm going to need one of you to tell me what 5 times 414 equals, please.
2070.
2070? Cool, okay. Then I'm going to identify another type of bond and break all those. So here we go. There's a CC bond there. Just one of them, so that's quite easy. CC up there, single bond, is 346. I'm being a good little mathematician and keeping my units and my tens and my hundreds and my thousands in columns because it makes it easier for me. Okay, it's something I'd suggest you do as well. There are more bonds in here, so I'm sorry my colour coding's not going to work too well, so bear with me on this. There's also a CO bond, and only one of them, so I need to find that, and that's another one that I haven't put up, but is in my data table over here. Single CO is 352. And again, there's only one of them. Okay, we've got an OH, which I did put up, so that's 464. Again, just one of them. And then I've got these 3 have all got an OO double bond, so I'm going to have to go 3 times. That's the double one, so 494. Again, I'm going to need one of you wonderful people to tell me what that equals. 1482. Okay, so I'm getting to the bottom of the board there, but now I'm going to do some really simple maths. I'm going to add all of those up, please. you get a value. So 2070 plus 346 plus 352 plus 464 plus 1482 equals
4,714.
4,000. Say it again for me, please.
4,714.
4714. Great. Okay, that's how many kilojoules per mole of bonds we've had to smash apart, break, for this reaction to occur. Now we go through the same process over here, and I'm not going to do it quite so slowly here, and I hope you can see what I'm doing. First of all, I'm going to have 4 times 724. This is from my CO bond. Okay? 1, 2, 3, 4. I have to make all of those. So I'm going to have that one. And again, need reliable sources for that number.
$2,896.
Thank you. I have got to make 1, 2, 3, 4, 5, 6 OH bonds, which we've said is 464. 2784. And that's it. That's all we've made. So again, I'm just going to add those up.
5680.
5680. Right. Now the enthalpy for this reaction is what we break minus what we make. Okay? So we should get a negative number because we know it's combustion, so it's exothermic. So now to find the delta H for this reaction, which normally has the subscript R for reaction, it is going to be 4714 minus 5680 equals
Negative 966.
negative 966. And don't forget our unit, kilojoules per mole, because there was only 1 mole of one of our reactants. Okay. If there was, say, 2 of those, our answer would be in kilojoules, and then to get it to kilojoules per mole, we'd divide the whole thing by 2. Okay, so you divide by whatever the number is in front of the first thing, basically. Okay. So that's how we use bond energy or bond enthalpy to work out the enthalpy of a reaction. And it's relying on a couple of things. One, that it's 1 atmosphere pressure, so you're looking at standard conditions, 1 atmosphere pressure, 298 Kelvin, those sorts of things. So there are a few assumptions made in this. So they won't be the values you'd get if you did it by an experiment, because you're going to have changes in state and so on. I didn't show the states of those in this case, but in this case they'll all be in gas phase. So it wouldn't be the standard enthalpy, because that's where I got the data from, in the gas phase. Alright, so bond energies, that's the last of our skills that we have to do for this achievement standard. So it's a good idea to do a bit of practice. There are some really good examples on page 144 that are worth trying. One that's quite similar to this one here, so I suggest you finish off on that.